Welcome to our 2022 EaRLap talk on early recall, late precision, multi-robot semantic object mapping under operational constraints in perceptually degraded environments. Semantic object mapping is the detection and localization of objects of interest using robust sensing systems in given environment. It is widely used in time-constrained, real-world scenarios, including disaster response, self-driving, science discovery, and agricultural harvesting. In this study, we focus on the DARPA Subterranean challenge. We seek objects of interest, which we call artifacts, such as survivor-related items and rescue resources, in perceptually degraded environments during multi-robot, human-in-the-loop autonomous exploration. The ultimate goal is to detect and localize objects in given environments while maximizing recall and precision within a limited time. Given the large scale of the environment, onboard power and payload weight limitation, narrow communication bandwidth, and low human cognitive load, the robot platform and the detection system are required to generate high detection accuracy while accommodating the limitations. We use the leg and wheel robot for this rescue task. Each robot is equipped with 5 real-sense cameras to maximize the field of view. We use the LiDAR point cloud to estimate the relative range from the robot to the observed object. Deep learning object detection models are running on a GPU. The rest of the components share the CPU with the autonomy stack. For the final competition, 8 ground robots are equipped with the same sensor configuration. A typical approach to address the semantic object mapping task is this. We pass the sensor data into detection algorithms on processors like GPUs, then transmit the result to another computer for localization. The results are then sent over the mesh network and finally reach the human operator for confirmation and submission. We initially maximize recall so as not to miss any true positive objects, but this results in too many detections and low precision. False positives are very common in these subtle environments. Also, a robot or a team of robots can visit the same artifact many times, and too many repetitions can overwhelm the comms network. Too many detections are problematic because we've got a series of constraints: computation, communication, and human cognitive load. We need some solution to prune false positives to increase precision. Our proposed early recall late precision semantic object mapping pipeline, EaRLap, is to reduce repeated and false positives before data transmission at 3 stages, which is our robot, base station, and operation. Objects detected with high recall in robot-gathered images are localized. Then false positives are pruned in various stages to respect network constraints before transmission to a base station. After the reconciliation of unique objects, an operator reviews detections to achieve high precision. In each stage, we apply different functions to perform detection and localization, and additional techniques to reduce data volume while maintaining the recall and enhancing precision. 7 subfunctions are designed for the subkey task. The EaRLap components are integrated into our robot and base station system. Now, let's look at each stage and the subfunctions. During data requisition, we select a subset of images with the best quality in the queue and maintain 5 Hz streaming. Object detection is the most critical stage because the source of data to pass through the filters starts from here. We want the model to detect all the artifacts and achieve 5 Hz detection rate per camera. Your low version 5 medium meets the requirement after being pruned by 70% to keep the strong detection performance and to be lightweight. The main dataset was collected from the robot cameras. To address the overfitting, we added 5% online generic data. This increased the precision and recall by 2 to 4%. We further reduced the number of detection using artifacts' unique features, like color and size, since the artifacts models are predefined by DARPA. Using our collected data, we define the color similarity range for some artifacts with distinct color signatures, like orange drill and red backpack. The scoreability is computed using color and size scores and the YOLO confidence. Applying scoreability significantly reduces false positives and so improve the precision. The precision gain is 16% in our test set. At the object priority stage, we reduce the data load by grouping detections into one instance. Each detected object will be only one report, represented by the instance with the highest scoreability. Reports with low scoreability are discarded. When the detection reports are received at the base station from different robots at different times, we reconcile them based on the place similarity and space proximity. To maximize the operator's confirmation effort, we show reports in the descending order of scoreability. In our operator interface, these yellow highlighted panels are quick access for different categories of detection results, ranked and grouped by scoreability. The blue box is one candidate report for submission. This candidate has 3 backpack reports sent by different robots and different times. Each image concatenation is 4 best images from different matrices. The last step of the pipeline is human confirmation. The UI allows the operator to modify the report in case of poor reconciliation. The subtle final event results, for example, the preliminary run, shows significant data reduction from 9,000 detections to 60 detection reports for the operator inspection. This reduces the original 19 hours of operator inspection time to 7.5 minutes. The precision increases while the recall is kept at 100%. Similar performance is shown in the final run. In conclusion, the EaRLap pipeline decomposes the problem into subproblems to achieve high precision and high recall under computational, communication, and human cognitive load constraints, and ultimately to provide high-quality information for human operators.